speak about twisted Ruelle zeta functions on locally symmetric spaces, the Fried's conjecture, and further applications. The stage is yours.
Hello, thank you very much for the invitation. I would like to talk about the twisted Ruelle zeta function on locally symmetric spaces, the Fried's conjecture, and further applications. The talk will consist of 3 parts. The first part will be an introduction. The second part will be concerned with Fried's conjecture and the non-unitary representations we consider. And the third part will refer to some further applications and results concerning the Fried's conjecture and the dynamical zeta functions. So I would like to start with the first definition of the Ruelle zeta function for a hyperbolic surface X. So this is a complex function with a complex variable S, defined for real part of S bigger than 1. By this product over the prime conjugacy classes in the lattice for the hyperbolic surface. And these prime conjugacy classes in the lattice correspond to the closed geodesics that they are prime. And this means that these geodesics, their length, cannot be written as a multiple of length of a shorter closed geodesic. So in analogy to the Riemann zeta function and the Euler product formula, here we have the prime closed geodesics, and here we have, for the Riemann zeta function, the prime numbers. And the precise analogy is for the Ruelle zeta function, we have this exponential e to the L gamma, where L gamma is the length of the prime closed geodesic. And here I have the prime number P. So in a way, the Ruelle zeta function is in a way a geometric analog of the Euler product formula. And so the Fried's conjecture. The Fried's conjecture in more simple words, for a hyperbolic manifold X and the representation rho of the fundamental group of the manifold, is concerned with the behavior of the Ruelle zeta function at the origin. So here the Ruelle zeta function is twisted by this representation rho of the fundamental group, defined for a big real part of the complex variable S. And here again I have it's defined via this product over the prime conjugacy classes which correspond to the prime closed geodesics. And I have this twist for the representation that I consider, and the determinant. So Fried found a relationship after proving meromorphic extension to the whole complex plane of this twisted Ruelle zeta function. And under certain assumptions for the representation, he proved that the modulus of the Ruelle zeta function at 0 is equal to the square of the Singer analytic torsion, which is defined by this finite product of regularized determinants of Hodge Laplacians on P forms. So here it's Hodge Laplacians on P forms and rho for the representation. It's a bit of confusion. And these Hodge Laplacians are restricted to the complement of the kernel. So we don't consider the 0 eigenvalue. So these regularized determinants are defined in terms of the spectral zeta function, which is another zeta function, and formally given as the product of the positive eigenvalues. But of course, because this is kind of considered like that, we define these regularized determinants via these spectral zeta functions. So this Singer analytic torsion is a spectral invariant. And this is an important result because on one hand, we have this geometrical zeta function, this dynamical zeta function. And on the other hand, we have this spectral invariant. So since there are many ways to study these dynamical zeta functions and these Fried's conjecture problems related problems, Fried in this paper where he proved this result, he used harmonic analysis on locally symmetric spaces, representation theory, and in particular the Selbert trace formula. Fried's conjecture and non-unitary representations. So I would like to introduce some geometrical setting, algebraic setting, considering a d-dimensional locally symmetric compact hyperbolic manifolds, which are given by this quotient of these Lie groups, where G is the identity component of the special orthogonal group, T, 1. D is an odd integer. K is the special orthogonal group. And we consider this identification of the real d-dimensional hyperbolic space with this quotient GK, the universal cover for my manifold. And gamma is a discrete co-compact torsion-free subgroup of G. Here, the co-compact assumption, so compactness, is essential. So here is some notation with all the Goth letters. Goth letter G is the Lie algebra of G. Goth letter K, the Lie algebra of K. Here is the Cartan decomposition of G. And Goth A is a maximal abelian subalgebra of P from the Cartan decomposition. A is a subgroup of G with Lie algebra A. And M is the centralizer of A in K. And is this special orthogonal group D minus 1. So in our setting, we consider the dynamical zeta functions associated with the geodesic flow on the unit tangent bundle of X, which can be identified by this quotient of these Lie groups, gamma G, M, where M is, as before, the centralizer of A in K, which is the special orthogonal group D minus 1. We consider gamma being co-compact, which means that every element apart from the identity is hyperbolic. And by an older result by Wallach, we know that gamma is conjugated in G to M gamma A gamma, where M is in M, the centralizer of A and K, and A is in the subgroup A, is stated here. So we consider chi finite dimensional complex representations of gamma, and sigma unitary reducible representations of M. And then we define the twisted dynamical zeta functions. So this is a definition for the twisted Ruelle zeta function, which is defined by this product over the prime conjugacy classes in gamma, which correspond to the prime closed geodesics of length L gamma. And here I have my representations chi of gamma and sigma of M. The twisted Ruelle zeta function is defined for real part of phase bigger than C, where C is a positive constant. This is non-trivial because one should use results from geometric group theory by Lubotsky and the by Lipschitz equivalence of the word metric on gamma and the hyperbolic distance. So this is not a trivial fact. And this is a definition of the twisted Selberg zeta function defined by this double product. So here I have the product over the prime conjugacy classes in gamma, and here the other product runs over K from 0 to infinity. And I have this additional term, which is the K symmetric power of the adjoint map restricted to n bar, the sum of the negative root spaces. Algebraically, but geometrically, this corresponds to the quadratic map of the Poincare map of the geodesic flow. So there is a geometrical meaning of this algebraic term here. Again, defined the twisted Selberg zeta function for real part of phase bigger than R, where R is a positive constant. So back to Fried's conjecture in more details. So the Fried's conjecture is concerned with the problem of finding a relation between the Ruelle zeta function at 0 and the analytic torsion, as it was stated by Fried in his paper Lefschetz formulas for flows. And by Chigin-Muller theorem, one can pass to a topological invariant, the Reide-Meisel torsion. And already this is a very nice and strong relation between geometrical objects and dynamical objects, such as the dynamical zeta function of Ruelle, spectral invariants such as the analytic torsion, and the topological invariant, the Reide-Meisel torsion. So Fried in 1986 proved that the Ruelle zeta function associated with an orthogonal representation chi of the fundamental group of a hyperbolic manifold of odd dimension. Then he proved that the leading term of the Laurent expansion of the twisted Ruelle zeta function by this orthogonal representation at S is equal to 0 is given by this term, where H is a number defined in pure cohomological terms, and in particular of these Betti numbers, so the dimensions of the cohomologies. And here I have the square of the Reisinger analytic torsion, defined as before by this product of the regularized determinants of the Hodge Laplacians on P forms. So some related work. There are several people working that work in problems related to this conjecture, to this problem of finding the relationship between the twisted Ruelle zeta function at 0 and spectral invariance, and topological invariance. Bucke and Olbrich extended these results for unitary representations of the fundamental group. And as well as Botsky, he considered more general representations of the fundamental group, non-unitary but very special ones, that they are arising as restrictions of representations of the group G. I would like also to refer to the work of Müller, Pfaff, Fedosova, and Susen, where more tools from representation theory are used and the trace formulas. And the so-called French school, where more tools from more dynamics are used, such as analytic, Larmouche, Aubet, Dank, and more. This is some analogies in a number theory, but I wouldn't like to refer more to this. Just I find it very interesting, and for those that are more interested, I would like to mention the book of Morishita, Notes and Primes, or the very nice articles of Denninger, where it's a whole program presenting analogies of the Ruelle zeta functions with zeta function with other zeta functions from number theory. But to the non-unitary representations of the fundamental group of the subgroup gamma that we consider. These representations chi of gamma are just finite dimensional complex representations and no other assumption we use. So we consider the corresponding flat vector bundle over X. And considering these non-unitary representations, the problem is that there is no Hermitian metric which is compatible with the flat connection on the flat vector bundle. And therefore, we have to deal with non-self-adjoint Laplace and Dirac type operators. So to overpass this problem, we consider these twisted flat Bochner-Laplace operators, denoted by this sharp here. These twisted Laplace operators are first introduced by Müller in his paper Selberg-Trace formula for non-unitary twists. So we consider these twisted Bochner-Laplace operators that are acting on smooth sections of twisted vector bundles. So tau here is a unitary and irreducible representation of K. So I have these twisted vector bundles. And these twisted Laplacians are acting on sections of these twisted vector bundles. So despite the fact that these twisted Laplace operators are not self-adjoint, are elliptic operators, which means that we can use the spectral theory provided by Shubin and use the fact that their spectrum is discrete and contained in a translate of a positive cone in C. So then one can consider the corresponding heat semigroups, the heat operator, induced by these twisted Laplace operators, and prove that it's an integral operator with smooth kernel. And since we are considering a compact hyperbolic manifolds, one can prove that this heat operator is a trace class. And so we can consider the trace of these heat operators and derive a corresponding trace formula. So this is a trace formula for the heat operator induced by the twisted Laplacian, but here I have this A sharp, which corresponds to a shift of this twist Laplace operator. So the left-hand side of this trace formula is the spectral side, which is the trace of this heat operator. And this is the geometrical side, the right-hand side of the trace formula. And one can see the volume of the manifold, and also here the length of the closed geodesics on the manifold. So using this trace formula for the heat operator, and rather a resolvent trace formula, so after some sort of manipulation of this trace formula, we can derive a resolvent trace formula, and then prove the meromorphic continuation of these twisted dynamical zeta functions. So for sigma being a unitary reducible representation of M, and chi a finite dimensional representation of gamma, we prove that the twisted Zellberg zeta function associated with sigma and chi admits a meromorphic continuation to the whole complex plane, and the singularities are described in terms of these discrete eigenvalues of these twisted Laplace type operators and Dirac type operators, and their orders are described by the corresponding algebraic multiplicities of these discrete eigenvalues. And then we can conclude also the meromorphic continuation of the twisted Ruelle zeta function, since there is a formula that relates the twisted Ruelle zeta function with the twisted Zellberg zeta function. So this is a determinant formula for the twisted Ruelle zeta function, where here we consider only a representation, a finite dimensional complex representation of gamma, chi. So there is no sigma representation. And considering the flat Hodge Laplacians, so Hodge Laplacians that they're non-self-adjoint but elliptic, associated to this non-unitary representation, acting on the space of K differential forms with values in the flat vector bundle associated to the representation. Then the Ruelle zeta function has this representation of this, considering these finite products of these regularized determinants of the Hodge Laplacians and a shift here, multiplied by this exponential, which involves the volume of the d-dimensional Euclidean unit sphere. And so also the singularity of the twisted Ruelle zeta function at zero, at s is equal to 0, is of this order, where d chi k is the dimension of the kernels of these twisted Hodge Laplacians. Back to Fritz's conjecture, but under this setting, so for non-unitary representations. So what we want is to prove that the Ruelle zeta function is regular at 0 and is related to this refined analytic torsion or the Capelle-Miller torsion. So the refined analytic torsion is introduced by Braverman and Capeller, and the Capelle-Miller torsion by Capelle-Miller. So initially one can say that they're not defined exactly in the same way, but we are talking about the same in spectral invariant, and there is a precise relationship between the two definitions. So today I would like to refer to the Capelle-Miller torsion briefly. So the Capelle-Miller torsion is defined in terms of this bicomplex, considering differential forms, vector valued differential forms. So this Capelle-Miller torsion is a combination of an element of this tensor product here for the determinant lines of the cohomologies, and the square of a Reisinger term, which is this term, which is given again as a finite product of these regularized determinants of these Hodge Laplacians. But here I have these twisted Laplace operators, these non-self-adjoint operators. So one can say that this formula is very similar to the formula that gives the definition of the Reisinger torsion, but the difference the difference here is that we are considering this flat Laplacian, so the operators are not the same. And the Reisinger torsion is a well-defined a positive real number, while this term that is involved in the definition of the Capelle-Miller torsion is a complex number. So the flat Laplacian is acting on the space of the K of the differential forms and is given by this formula. I would like to mention here that this is, again, one can say that we are not talking about the same Hodge Laplacians, since this operator here is not the adjoint of the differential with respect to the Hermitian metric on the flat vector model. So this is not the adjoint. So we're talking about a different Laplacian, this twisted Laplacian, and this term that gives the Reisinger term in the Capelle-Miller torsion, it's not the same, it's a complex number. So back to Fried's conjecture. So the goal is, what we want is to find this relation between the twisted Ruelle zeta function at 0 and this complex analytic torsion, this new analytic torsion. The problem is that since we are considering non-unitary representations and non-self-adjoint operators, the Hodge theory is not applicable, which means that there is no isomorphism between the kernels of the Hodge Laplacians on K-forms and the cohomologies in the flat with coefficients in the flat vector model. So, which means that we somehow are not able to use this determinant formula that already one can see that some product of determinants of Hodge Laplacians are there in the formula, and somehow one can do no more things, and there's no somehow possibility to use this determinant formula to conclude some results from some recipe for analytic torsion. So a solution to this problem is to consider the formations of acyclic and unitary representations of the fundamental group. So this is the set of all complex representations of the fundamental group of the manifold of this odd dimensional hyperbolic manifold we considered, which is complex algebraic variety. And considering the set of all acyclic unitary representations of the fundamental group, we consider an open neighborhood of the set of the acyclic and unitary representations, such that an operator, the odd signature operator, is bijective. The odd signature operator, the square of the odd signature operator, gives exactly this twisted Hodge Laplacians on K forms, which means that for this neighborhood of the acyclic and unitary representations, the Hodge Laplacian is injective, so we don't have the zero eigenvalue, and then one can use this determinant formula in the sense that if we consider s is equal to 0, then this exponential goes to 1, this is 0, and then we end up with a formula that gives exactly the Capelle-Miller torsion, which corresponds to this term, the Reisinger term. Hence, we can conclude that for the representations, the non-unitary representations that belong to this open neighborhood, the Ruelle zeta function is regular at 0 and is equal to the complex Capelle-Miller torsion. I would like to also mention results and extensions by Müller and Susen for a higher rank locally symmetric spaces. I would like now to move to part 3, some further applications. So one can ask why we have always this assumption that the dimension of the hyperbolic manifold is odd. One certainly can consider even dimensional hyperbolic manifolds or complex hyperbolic manifolds and use tools such as the Selberg trace formula to study these dynamical zeta functions. So the problem is when we want to consider more general locally symmetric spaces of rank 1, such as hyperbolic manifolds of even dimension. The problem is that by Harish-Chandra theorem, we have also the presence of the discrete series representations, and then the corresponding trace formulas are way more complicated. So starting from compact hyperbolic surfaces, so for dimension 2, which somehow one can say, can guess that is the less complicated case, but also it seems to be an interesting case. So considering compact hyperbolic surfaces, we define the twisted Ruelle zeta function, again by this product over the prime conjugacy classes and gamma, and considering non-unitary representations chi of gamma, defined for real part of S bigger than a positive constant, and correspondingly the twisted Selberg zeta function for chi being a non-unitary representation of gamma. Here I have again a double product over K, over the prime conjugacy classes of gamma and over K. So in order to study the twisted Ruelle zeta function, we can study the twisted Selberg zeta function by this relation here of the two twisted zeta functions. And together with Jan Fraum, we proved that the twisted Ruelle zeta function associated with a non-unitary representation of gamma admits a meromorphic continuation to the complex plane. Moreover, there is some interesting behavior of the twisted Ruelle zeta function at 0, and is given by this way. So it's given by these terms here, where we can see also here the dimension of the representation space, of the representation chi we consider, as well as some hidden Euler characteristic here. So again, one can see that the behavior of the twisted Ruelle zeta function at 0 is related to some topological invariants such as the Euler characteristic. So here we consider, in order to prove this result, we consider the Selberg trace formula. We prove the Selberg trace formula for non-unitary twists. One can see here the non-unitary representation by here, the spectral side of the geometrical side, excuse me, of the trace formula, by the dimension of the representation space as well as the trace of the representation. And again, we use rather a resolvent formulation of this trace formula to prove that the twisted Selberg zeta function admits actually a holomorphic extension to the whole complex plane, and then conclude that the twisted Ruelle zeta function admits a meromorphic continuation. This interesting result about the asymptotic behavior of the twisted Ruelle zeta function at 0 comes from the functional equations for the twisted Ruelle zeta function after proving meromorphic continuation. Also, as further applications and further results, we also consider together with Jan Fraum and Leo Bernard compact hyperbolic Orbis surfaces. So here we consider Orbis surfaces X, and the unit tangent bundle of the Orbis surface is a Cypher fiber space over X, is given by this gamma quotient PSL2R. And we consider the twisted Ruelle zeta function associated with the representation rho, non-unitary in a GL VI rho, irreducible. And under certain assumptions for this representation, we managed to prove that the Ruelle zeta function at 0, the twisted Ruelle zeta function at 0, associated with this representation of the fundamental group on the units of the unit sphere bundle, is given up to a sign to is equal up to a sign to with the Reidemeister derived torsion of the unit sphere bundle. So this was this result that is proved again using a Hilbert trace formula. But the situation here is a bit more complicated since we consider Orbi surfaces. So in my lattice gamma, we allow also elliptic elements, and the Hilbert trace formula is rather more complicated, and it looks like that. So this is the trace formula for Orbi surfaces. Here one can see that again we have the two sides, the spectral side and the geometrical side. In the geometrical side, we have again the terms that correspond to the identity contribution plus the term that corresponds to the discrete series representations. The terms that corresponds to the hyperbolic contribution, which looks pretty similar to the term of the trace formula, the geometrical side of the trace formula for surfaces. So it's pretty similar. And then there is this extra term that corresponds to the elliptic elements. And this is actually the term that gives rise to the topological torsion. I would like to mention also that in this case, in the case of the Orbi surface, we didn't use any notion of analytic torsion, or we didn't use for deriving this result concerning the special value of the twisted Ruelle zeta function at 0. We didn't use somehow the spectral side of the trace formula and notions referring to analytic torsion. So it was only this topological Reidemeister-derived torsion appearing. So here I would like also to mention another application, which is related to the twisted Hilbert zeta function for hyperbolic surface. So here we consider again compact hyperbolic surfaces, and the twisted Hilbert zeta function given by this way, with this double product. So using the previous results for the holomorphic extension to the complex plane of this twisted Hilbert zeta function, so using this result, one can prove some interesting result concerning the study of the spectrum and the bottom of the spectrum of these twisted Laplacians. So we can prove that considering the critical exponent delta of the representation rho, so rho is again just finite dimensional complex representation of gamma for my surface. So we define the critical exponent by the infimum of this real number here, S, such as I have this convergence. So basically this critical exponent is a number that gives the domain of the convergence of the twisted Hilbert zeta function. So if we define the parabolic regions, these parabolic regions associated with this number sigma in this interval, 1.5 plus infinity, then this joint work with Frederic Knott, we proved that these twisted Laplacians defined as above, so it's a matter of notation here, it's a sharp missing, but we refer to the same twisted Laplacians. So these twisted Laplacians defined as above, then we have that the spectrum of these twisted Laplacians is always included in these parabolic regions, but here I have these parabolic regions associated with this critical exponent of the representation. And this is again due to the holomorphic extension of the twisted Hilbert zeta function using the trace formulas. So one can say more about this result and be a bit more explicit. So in particular, one can one can somehow prove, give a more explicit the bottom of the spectrum for these twisted Laplacians, in the sense that one can prove that this bottom is given by the number delta, so this critical exponent multiplied by 1 minus delta. And I guess here I would like to stop. Thank you for your attention.
Yes, thank you very much, Dina. We can thank the speaker. So we have time for questions.
Also a bit faster.
So does anyone have any question? Please don't hesitate to unmute yourself. So I was wondering it seems to me like in every time you use the trace formula, you were using the heat kernel. Can you use other kernels?
All right, so I guess you ask if one can consider different operators as a heat than the heat operator, such as wave operators. And so initially, in the paper by Muller, Selberg trace formula for non-unitary twists, the test function belongs to this Paley-Wiener space. So then there was this result by me for the heat operator. So this different test function, which is not compactly supported, but nevertheless I have this nice decay, so I can use this test function. So I guess yes.
Okay, so you need some regularity, some decay assumptions.
Yeah, exactly. Yeah.
Okay.
So for compactly supported test functions, I guess. Yeah.
Okay. So there's Clara who has a question.
Yes, thank you. Yes, hi, Xenia.
Hi,
How are
Clara.
you?
Fine.
Yeah, good. Yes, so I wanted to ask. So when you consider these Orbi surfaces, are you taking some particular case, or is like more general? And so which order are you taking for the elliptic elements?
Yeah. So
does that make sense? Yes, the question.
Yeah. Yeah, it's there are certain assumptions considering this representation. First of all, we consider compact hyperbolic Orbi surfaces, which is already an assumption. And then, yes, I mean, so the main assumption we consider is that it is so this is cyclic. We consider cyclic representations, but this is related to the representation for the elliptic elements. So this is hidden here somehow. So rho of t is known the identity. So this is cyclic assumption is essential. Yes.
Okay. So it could be like any order, or is some particular order?
No, I don't think that should be a particular order. No.
And do you see like the cone angles somewhere, or?
Excuse me, which angles?
The cone angles, are there cone angles showing up somewhere?
Oh, I guess you mean some singularities or.
Yes. Well.
So well, I don't know. I don't know if there is more like.
Well, let's say the order of the elements, whether they are shown somewhere in the formula. It's more precise.
I think that in particular there is no particular like geometrical assumption, I will say, or something particular concerning the elliptic elements, as you ask the order and so on. Rather, we have these assumptions for the representation, which is essential. And I mean, I said that the analytic torsion or the spectral side of the trace formula.
So it was topological, no?
Does not play so much role, but also I have this, you see, like these terms which are quite analytic and it's smart of computation at the end. So why this topological torsion appeared from this term? So I don't know if it makes sense to I know your question. I don't know.
Exactly. I also don't know if my question made much sense.
Maybe you can explain to me more, but I guess it. I mean, at the end of the day, this trace formula or the resolvent trace formula, in a nice, not exactly miracle, but in a nice way, the topological torsion is given exactly after some formulation of this trace formula by this term that corresponds to elliptic elements. So I don't know if it's there is some geometry that plays some role in. I mean, you say like if there are some certain assumptions, what you asked more and so on. We have certain assumptions for the representation. This is
Okay.
Thank
And
you.
Amir, I mean, is this Amir? You had a question?
Yeah. Hi. Thank you for the talk.
hi.
Yeah, it's a silly question. So basically, I do one thing in my life and I do it every time. And I have a question if you can do it for this one. So from this trace formula on the screen, can you recover the twist or recover the, like, if you know this trace formula and you don't know what the representation is it a silly question to ask? It's like an inverse problem?
Inverse problem meaning
So you have this heat trace, or you could also make a wave trace out of it. I think maybe like Laura was suggesting. And basically, I've always done this stuff where you look at the wave trace or you look at the heat invariance at 0 or something like this, and you see if you could recover the twisting.
the representation, you mean?
Yeah, the representation itself.
So knowing, like having in hand these trace formulas to have information about the representation.
I mean, more than just the torsion, for example, or maybe different from the torsion.
I guess it's a very nice question. I don't know. It sounds to me a very interesting question, but
I mean, I'm just thinking, for example, if you know something about the length spectrum or something, probably there's some kind of Poisson relation here coming from the Selberg trace formula, and maybe you could read off from the coefficients, for example, on that thing. You know, at least what the twisting does on you know each homotopy class or something. I don't know.
Actually, it's a nice question. I think it's a nice question in general, although I don't have an answer. The only thing I can comes to my mind is like this Lubotsky results that I mentioned, that we have, like, in order to prove the convergence in some right half plane of the twisted dynamical zeta functions, we consider this bound for the modulus of the trace of these non-unitary representations. And then this is given, so the lengths of the closed geodesics are involved. So I don't know from the trace formula rather than from this result.
Yeah.
One can guess something. I think usually what we do is the other way around, like having some assumptions for the representations to conclude something either for the geometry or for the geometrical objects such as the zeta functions, or the spectrum such as the bottom of the spectrum. So I guess it's the other way around, but I guess these Lubotsky results might be an answer to your question, but I'm not quite sure.
Sure. Yeah, no, thank you. Appreciate it.
Is there anyone else who had a question to ask the speaker? In that case, I think we can thank the speaker again.